Welcome to the LANDFIRE and California Fire Science Exchange webinar. I'm Jeannie Patton, Communications Lead for the Nature Conservancy's LANDFIRE program, and this is one of a series of webinars offered in partnership with the Fire Science Exchange Network that look at LANDFIRE's Biophysical Settings Review project. Today is the fourth of our series with California, and other regional presentations are scheduled through the spring, with more coming in the autumn. Today's presenter is Kori Blankenship, fire ecologist with the Nature Conservancy's LANDFIRE team. Kori joined TNC in 2005 when she was hired to facilitate the creation of thousands of vegetation dynamics models for ecosystems across the U.S. She earned undergraduate and graduate degrees in geography from Western Washington University's Huxley College of the Environment. Graduate research investigated seasonal changes in fire behavior and effects in the dry forests of north central Washington state. Kori worked as a GIS specialist at the Missoula Fire Sciences Lab and as a wildland firefighter in Washington and Colorado for the Park Service and the U.S. Forest Service. Her current focus is on taking the results of the first 5 years of the LANDFIRE project and applying the processes and products toward addressing conservation challenges on large landscapes and ecosystems. Kori lives in Bend, and she is one of the leaders on our Biophysical Settings Review project. Thanks, Kori. It's all yours.
All right, great. Well, good afternoon, everyone, and thanks so much for taking time out of your busy schedules to be here. I'm going to start just with a really brief introduction to the team I work with. This is the Nature Conservancy's LANDFIRE team. We are one of the partners on the LANDFIRE program. We work with the mapping teams at the Missoula Fire Science Lab and the USGS. Our team is specifically responsible for education and outreach for the LANDFIRE program, and we facilitated the development of the LANDFIRE biophysical settings models that we're going to be talking about today. Here's our agenda for the day. I am going to spend a good amount of time at the beginning talking about the fundamentals of BPS models so that everybody understands what they are and what they do. Most people use spatial data in their day-to-day work, but we find that not as many people know about the BPS models, and so I just want to provide some basic information up front so we're all on the same page about that. Then we're going to talk about using the BPS model, both within the LANDFIRE program as well as how users outside of the LANDFIRE program have used these data. And then I'll end with a little bit of information about the BPS review and our ongoing efforts to improve the BPS models. So we'll just kick off here with my take-home messages. I had a debate coach in high school who said, you tell them what you're going to tell them, you tell them, and then you tell them what you told them. So here's what I'm going to tell you or hope to convince you of today. These models are really important. They're important because they help us understand complex ecological processes. They really focus in on the successional and disturbance dynamics of ecosystems around the country. And they also, as I'll show in a later example, provide a framework for exploring alternative approaches to achieve management goals. And so I hope that you'll see throughout this presentation these themes and how important the models can be in a management context. All right, so let's jump right in. I think there's no better way to understand how these models work than to dissect one. And actually today I'm going to dissect two, but we'll start with the Southern California coastal scrub. A LANDFIRE BPS model is actually two things. There are two parts. First, there's a description document, and second, there's a state and transition model. And together, these two things describe the basic ecology of an ecosystem prior to Euro-American settlement. So let's take a look first at the coastal scrub description document. And I'm going to have Stacy drag over my PDF so that you can see it. Here we go, Southern California coastal scrub. So this is the first part of what makes up a BPS model, and it's just a description in English. You can see at the top the people who contributed to the information in this model. You get information about the geographic range, as well as the biophysical site. And then as you scroll through, you get more information on the species that you might find in this ecosystem, the disturbance, and the disturbance description not only includes information about fire, but really any disturbance that's important to the dynamics of the particular ecosystem that's being described. And then you find information about fire frequency. These are actually results that come out of the state and transition model, which is that second part to the BPS model. You'll find information about issues and problems. This section will often list things like assumptions that go into the models or problems that the modelers encountered, maybe some limitations that they found. You'll find information about what we call native uncharacteristic conditions. And what that really means is conditions that you're going to find on the ground today that you would not have expected under the reference condition. Because again, these models are describing pre-Euro-American settlement ecosystems. But there is this one section that will sometimes mention things about invasive species and so on. Okay, and then the next section, major section, is this part that we call succession classes. And this is the real link between the description and the state and transition model. Each biophysical setting gets broken down or divided into succession classes, or you might think of them as serial stages. And these are the stages of development that that biophysical setting goes through. So you can see here that the coastal scrub starts with an early development stage. There are some indicator species and a short description of what that phase looks like. There's a mid-development stage, and then down here is the late development stage. And I'll get into a little bit more detail about this when we look at the state and transition model, but I just want you to know that there is this description here. And then the descriptive information ends with this section of references. Okay, Stacey, let's drag this aside and we'll get back to the PowerPoint. Okay, so that's the description document. And here is a picture of what the state and transition model looks like. This is a model that was developed in what's called the Vegetation Dynamics Development Tool, or VDDT. That model has since been superseded by what's known as STSIM. That's our current modeling software. If you prefer VDDT, you can still use the models in that format, but we're trying to move over to STSIM because it has some additional functionality. So here's what the model looks like. These boxes represent the succession classes for this coastal scrub system. You see that early development phase, the mid-development, and the late development. And each of these, again, were described in that description document we just looked at. You can see that there is an age range associated with each box. So early lasts from 0 to 5 years, the mid from 6 to 25, and the late from 26 to 200 years. There are transitions that describe the successional pathways then between these states. And this one just follows a very predictable successional trajectory from the early to the mid to the closed. We also define pathways for disturbances in these models. This particular model just has replacement fire, but we'll model anything that's important to the ecosystem. In the southeast, we've modeled hurricane disturbance. On the Great Plains, we've modeled prairie dog disturbance. And here in the coastal scrub, the replacement fire is the key disturbance. So you can see the pathways that fire takes in this model and the return interval for those disturbances. In this case, it's occurring on average about every 150 years. It'll reset your early class, or if you're in the mid or the late close, it'll take you to the early one all. Now, we take this model and we run it out over time to estimate the percent of the landscape that would occur on average in these successional states over time. In this particular system, you can see that the landscape is typically, under the reference condition, going to be dominated by this late one closed class. About 80% of the landscape will be there, perhaps 15% in the mid one closed, and 5% in the early. This becomes a reference condition or a benchmark then against which we can measure vegetation change over time. So this is one of the important outputs from the model, and I'll show you another one in our next example. Okay, so now let's take a look at a slightly more complex model. This particular model is for the Mediterranean dry mesic mixed conifer forest in California. And here's what its state and transition model looks like. It's defined by 5 states, starting with an early one all. You have a mid-open and closed state and a late open and closed. And again, you have an age range defined by these numbers at the bottom of each class or box that tells how long that class lasts. And Stacy, if you'll drag over the document one more time, we'll take a look at some important information that defines each of these states. So here we are looking at the description that accompanies this dry mesic mixed conifer forest model. You can see again the folks who contributed it to at the top, and I'll just give a shout out to Joe Sherlock because I saw his name in the participants. So thanks, Joe, for being here and for contributing to the models. If you scroll down through this document to the succession class section, you can see what it means to be open versus closed. So let me go to the Class B description, and notice right here this structural information. This defines the cover and height associated with a particular successional class. So the mid-closed state is defined as having 50 to 100% canopy cover and trees 10 to 25 meters tall. Now if you scroll down and look at that same information for Class C, the mid-development open, you see that the canopy cover is 0 to 50 for that same height class of trees. So that 50% mark then is your canopy cover cutoff, which defines the difference between the open and the closed. And that's going to vary model to model. And so again, you need to couple the descriptive information with the quantitative information in the model to understand fully what's being described. Okay, Stacey, let's clear this one. Thank you. Okay, so now let's take a look at some of the pathways here. These are the successional pathways. The predominant successional trajectory follows the closed classes, but there are alternative successional trajectories in this particular model that have probabilities associated with them that can, for example, take you from the early one all with a low probability to mid one open or to the mid one closed. There are also 2 important pathways that take you from the mid one open and the late one open to their corresponding closed classes, and those are happening in the absence of fire. So what this transition here says is that if you're in mid one open and you go 32 years without fire, you're going to transition to the mid one closed state. So those are the successional and the alternative succession pathways associated with this mixed conifer model. There are also a number of different fire disturbances in this model, and I've just listed the most frequent fire pathways in this model. I didn't put the fire return interval for every single pathway because it was just getting so crowded. But you can see that we break down the fire disturbances into their different severities. So we have a different probability associated with surface fire, mixed fire, and replacement fire. And whereas you saw in the coastal scrub only replacement fire was used, in this mixed conifer forest, we're using all 3 different fire severities. The most frequent fire is the surface fire that's maintaining your mid and your late open states. There are also insects and disease probabilities in this model, and the insects and disease probabilities or pathways are being used to either maintain states or, in the case of more severe insect disturbances, to open up your closed states to a more open state. So again, if we run this model out over time, which we do in LANDFIRE because we're interested in these reference proportions for the different classes, you can see that the dry mesic mixed conifer is really going to be dominated by your mid one open and your late one open. So those open classes dominate the reference condition for this particular model. You can also get fire return interval information. For this particular model, when you combine all of the different fire severity, surface mixed and replacement, you get an overall fire return interval of about 11 years. And I know these graphs are a little bit hard to read, and that's okay, because what I really want you to see is that there's some variability happening over time. This is because this model is stochastic. So you are going to get some variability in your disturbances over time. It's not just the probability that you put in that's simulated. Okay, so that's the introduction to the models, and now I want to talk a little bit about how these models were created. And I really like talking about the LANDFIRE biophysical settings models because this product, more than any other LANDFIRE product, really belongs to the user community. At the beginning of each description document, I showed the authors for the models. The LANDFIRE program was just facilitating the development of the models. We went out and we held workshops, and we got hundreds of experts and managers and ecologists to help us describe these ecosystems and model them. So that's how the models were developed. These models, like any other data product, have their strengths and weaknesses, and I want to make sure that we cover some of those here today. These are kind of the highlights. One of the great strengths of the models is that they cover over 500 biophysical settings. There's one for every single biophysical setting that LANDFIRE maps. In some cases, you get multiple models for one given biophysical setting, and that's so that we can describe how the ecosystem might function differently throughout the geography in which it's represented. So, for example, ponderosa pine in the northern Rocky Mountains is going to have a different model than ponderosa pine in the southern Rocky Mountains. So we cover grasslands, shrublands, and forested biophysical settings, and that's one of the great strengths of this data set. Another strength is that the models are connected to spatial data. So every single model represents a biophysical setting. Each biophysical setting is mapped on the ground, and we even map the different states. So each box in the model has a map or pixels that are associated with it on a map that we call succession class that shows where that particular succession class is located on the ground today. There's a connection between the model and the spatial data, which is quite useful. Another strength of the models is that I think they're relatively easy to use, and even if you don't buy it, even if you don't want to take my word for it that they're relatively easy to use, at least they are supported by the LANDFIRE program. So you can call us and get help using the models, or you can use the information that we've put online. We have a number of tutorials and guides that help people to use the LANDFIRE models as well as the other spatial data. There's good documentation with these models. So we don't just hand over a model with a bunch of numbers in it. As you saw, there's a description document that helps you understand those numbers, the assumptions behind those numbers, how we came up with them, etc. That's very, very valuable. And then these models are really suitable, and they were developed for large landscapes, which is great if you're working at a large landscape scale. If you're not, we encourage people to refine them for local use. Okay, let's look at some of the limitations then now. The LANDFIRE models are reference condition models, and they don't include any current management transitions or information about climate change. A number of different folks have taken the models and added that in. So you can definitely do that in the STSIM modeling environment, but the LANDFIRE models, as you will get them from landfire.gov, don't include that information. Another limitation is that the LANDFIRE models use a number of modeling constraints. We had to have some limits on what people could do when we developed this modeling set, and that was to ensure consistency across the entire country. So, for example, one of our modeling constraints is that we never allowed people to model or define more than 5 successional classes for a given biophysical setting. You can adjust the model if you want to. I have been working, well, I worked last year with a forest in North Carolina, and they wanted to add some old growth states, and so we added that on to an existing LANDFIRE model. Another item that's perceived in some cases as a limitation, although this depends on your situation, is that the models are non-spatial. Now, the benefit of being non-spatial is that the data requirements and the user skill to use them is perhaps not as restrictive or limiting, so that can be a good thing. On the other hand, if you have good spatial information, clearly you can use that, because a lot of ecological processes are spatial, and you want that information. So the STSIM modeling software will allow you to bring in spatial information if you want, but the LANDFIRE models aren't inherently spatial themselves as you get them off the shelf from LANDFIRE. One of the limitations of all biophysical settings models is that they're difficult to validate. There's limited information to build them. And so sometimes in the description, you're going to find text that will say, well, there wasn't very much information, or there was disagreement on, say, the fire return interval for this ecosystem. And then again, we just encourage folks to refine these models for local use, or at least review them to make sure they're applicable to the landscape you're working on. Now, within LANDFIRE, we have a number of different ways that we use the biophysical settings models information. As we showed with some of the results, we generate fire frequency and severity information from the biophysical settings models, and we use that then to map fire frequency and severity across the landscape, and then we group that into the fire regime classes that you see here. So this information is coming directly from the biophysical settings models. We also, in the model description, have that rule set, that structural information that defines what cover and height is associated with a particular succession class. That becomes the rule set by which we map succession classes on the landscape today. And that information then can be compared to the reference condition that's generated from the model, and we map vegetation condition class from that. So there are a number of really important ways that LANDFIRE spatial data are tied to the biophysical settings models. Now, just to back up for a moment, I want to talk more broadly about how conceptually this information can be valuable in a management context. This figure is one that I took from a chapter in a book by Weems et al., and the chapter was written by Hugh Stafford and others, and I just think it's a really elegant explanation for why this historical information is still valuable today in the face of a lot of uncertainty about future climates and what that's going to do to vegetation. So the way this graph works is it's showing range of variation on the y-axis, and across the x-axis are a number of different management strategies. So, for example, if your historic, current, and future range of variation all overlap, you may be in a situation where you simply want to maintain your current vegetation. If your current condition is very different than your historic or your future, you could be in a restoration type situation. If the past and the current are fairly well aligned or overlap, but your future looks quite different, you could be in an adaptation situation. If the historic is quite different than where you are current, but the current overlaps with the future, you may want to maintain rather than restore. And then if you are in a situation like this last one on the right, where none of the situations align, but the historic condition is more closely aligned with the projected future condition than the current, you might be in a restoration and then adaptation type scenario. So I don't want to imply in any way that the historic condition or the reference condition that's presented in the LANDFIRE models should be the desired condition for a given landscape. It's just a piece of information. It provides context that, when taken into consideration with your current and your projected future conditions, can be quite useful. Okay, now let's take a look at an actual real-world situation where these models were used. The models have been used in a number of different management contexts around the country, but I really like this Bodie Hills case study because I think it highlights how the models can be used in a collaborative sense that's been quite valuable. This is some work that was undertaken by our colleagues at the Nature Conservancy of Nevada, Louis Provencher, Greg Lowe, and Susan Abel, and they used the vegetation condition class metric and the BPS models as a component of a conservation action plan where they were trying to improve ecological conditions, reduce fire risk, and maintain livelihoods in this Bodie Hills landscape. Here is a map of that particular landscape. It's on the east slope of the Sierra Nevada, right on the California-Nevada border. It's about 192,000 acres. The BLM is the primary land manager here, and you can see the gray squares are private lands. There's about 30% of the landscape in private ownership. There are very few invasive species on this landscape, but there is some cheatgrass, particularly along roads and at lower elevations. That was a concern and something that was dealt with in the modeling effort. And there's also a large genetically distinct population of greater sage grouse that was a conservation concern here. So for this planning process, the folks that I mentioned at the Nature Conservancy used a technique that they developed called landscape conservation forecasting. And the way it works is they bring in stakeholders and they use BPS models to model current conditions and compare that to potential future management scenarios that they develop collaboratively. You can see here that the predictive ecological models, and by that they mean LANDFIRE Biophysical Settings models. They took LANDFIRE Biophysical Settings models and then adapted them with a lot of local information. They use those to compare a current management, they compare what they call a minimum management scenario, which is basically acts as a control. If we do nothing, what's the landscape going to look like? That's their control. And they compare that to their modeled alternative scenarios. And again, in this case, they had an ecological scenario and a fire risk reduction scenario. The final step then is to do a return on investment calculation to see where they can get the most bang for their buck in terms of the management investment and the predicted vegetation conditions. So again, they start with the LANDFIRE biophysical settings models. They adapted them with local information to make sure that they better represented their particular conditions right there in the Vodi Hills. And then they added information about the management actions that they wanted to test and the costs associated with those actions. Then they ran the model out to see what impact the management would have on the vegetation states over a 20-year planning time frame. And these are some of the results. So what this particular table shows is the ecological system or biophysical setting, the current condition of that ecosystem, and that gets mapped from satellite imagery. Then they have their modeled 20-year no management scenario. This is their control, and the 20-year ecological management scenario. And the colors here represent the condition of the vegetation. So compared to the reference condition, you can have a low departure, a moderate, or a high departure. Also, I want to point out before we look at the details here that a number of systems under the ecological management column have an NA, and those are systems that were either very, very small, so they decided not to run this management scenario out for them, or they're systems that are mosaicked with other systems and they're managed along with them. So they might be represented by some other ecological system in the table. Okay, so let's just take a look at a couple of these. Let's look at the aspen. Currently, or when this analysis was done, it was moderately departed from its reference condition. If they did nothing for 20 years, its condition would decline slightly. But under the ecological management scenario, they could restore it to something somewhat closer to that reference condition. The montane sagebrush steppe starts out with much higher departure, and it actually might improve with 20 years of no management, or at least it's not getting any worse. But under the ecological management scenario, they can improve that condition somewhat. And then there are other systems like this Wyoming big sage down here at the bottom, the sandy big sage, where even under their ecological management, they're not able to improve the condition of the vegetation very much. So this information becomes the basis for evaluating the different management strategies and a key factor in determining where and how to invest the resource restoration dollars that they do have. With this information then, they developed the Conservation Action Plan for the area. And in that Conservation Action Plan is a table like this for every single ecosystem. This one's for the montane sagebrush steppe. There's a specific objective for each ecosystem. In this case, they're looking at reducing departure, preventing an increase in their high-risk classes, and I believe what that's referring to is the spread of invasive species. And then they're going to put in a fuel break around the Vodi State Park. You can see there are very specific actions. I've just called out a few, some early spring burns, RX fire and open classes. Notice they're referencing specific states in the model here where these actions are taking place, and then those can be tied to specific conditions on the ground. They have a target number of acres that they want to achieve each year for each action. Here we go, trying to get my pointer. So here are the acres per year, and a specific cost per year. And from that, they're able to get the total cost for the actions defined here. Okay, so within months of completing this project, the Fish and Wildlife Service provided over $100,000 of stimulus funding to restore wet meadows. And these are some pictures before and after of a wet meadow restoration project that was done on private land. And this project was specifically funded because there was this stakeholder plan that was developed collaboratively in place. Now, last time I talked to Louie, the BLM was still getting its environmental assessment reviewed. So I'm not sure the status on the BLM land, but at least there's been progress on private lands within this landscape as a result of this Conservation Action Plan being developed. Now, the models really aren't the answer here, but hopefully what you can see is that they provide this structured framework that facilitates people working together, even people that have been adversaries in the past. So folks can come together, they can look under the hood of these models, share ideas about how the ecosystems work, test hypotheses very quickly, and learn together about how these ecosystems function and how they can be managed. Okay, and so finally, I want to touch on the review process that was mentioned earlier. The LANDFIRE biophysical settings models, as I said before, are really owned by the LANDFIRE community. They were created by the LANDFIRE community, and now we have an opportunity where we are seeking additional input from the user community to help us improve these models. They have been languishing on the shelf since they were finished in about, I don't know, 2007 maybe. And we know that there has been new science and new information that could be used to improve the model set. And there are probably some errors that need to be created. And now we have this opportunity over the next few months to refine this model set and update it. And so we've developed a very simple process where we're asking folks to go to landfirereview.org and learn about the review process. It'll just take, maybe 20 minutes. On that website, you can download a description document, and those description documents are exactly what I showed you today. It's a Microsoft Word document. They're typically 5 to 10 pages long, and we ask people to turn on track changes and give us some feedback. Can you bring in information from more recent studies that weren't included in the original description? Can you add anything to the description that's already there? Do you see any errors? Can you add new references? That kind of thing. And I think that the amount of time that it takes per review is going to vary a lot by BPS and by the reviewer, but I would guess on average it might take an hour to review a biophysical setting. So we're not asking for a huge amount of time, but if you have time and know some particular ecosystems well and can provide review, we would really appreciate that. Once you've done your review in Word, we just have you email it back to us, and we'll offer our most sincere thanks for helping out. Okay. And here we are back again at the take-home messages. The LANDFIRE model set is far from perfect, and I'll be the first to admit that, but it's very, very useful. And I think that it's been particularly useful on landscapes where folks are interested in really looking at how ecological processes work and how management actions function within the basic ecology of an ecosystem. With the models, you can tie into the spatial data to actually tie the ecology to a specific place on the ground. And again, the models cover all the ecosystems that LANDFIRE maps, whether they're grass, shrub, or forests. So with that, I'm going to pass it over, I believe, to Jeannie to wrap it up, and then we'll take some questions.
Hi, we want to let you know how many different ways you can find LANDFIRE online. The LANDFIRE program home is landfire.gov. I think most of you have been there, and if not, take a look. The Conservation Gateway is the Nature Conservancy's website where the LANDFIRE site lives, nature.ly.landfire. Our Twitter handle is at nature_landfire. Our YouTube channel is LANDFIRE Video. In addition to our webinar postings, you'll see, I think, between 75 and 80 other videos there, so we invite you to take a look and let us know if you'd like some other kinds of videos, tutorials, how-tos, whatever. We'll be glad to work with you on that. Our bulletin comes out every other month, and we send postcards as we have news of releases. You do need to opt in. If you don't have time to write down this URL, contact me directly at landfire@tnc.org, and I'll send you the information, and you can log in that way. And don't forget our BPS review website, landfirereview.org. landfire.org. You'll find everything you need to know, including FAQs and starting you from scratch on the BPS review. Again, your default is landfire@tnc.org, and we hope to hear from you soon.
Oh, great. Okay. Where can the BPS description document shown earlier be located online? I found the Access database, but not the description document. Okay, this is a great question. On landfire.gov, if you go to the BPS models download page, you're going to find a couple of different products. You can download descriptions as PDF documents, or as this caller mentioned, you can get them in an Access database. The Word document that I showed you is actually a document that we produced for the review, and that is available from landfirereview.org. And so for the Word document, go to landfirereview.org. For a PDF or an Access database, go to landfire.gov. And let's see if there were any other questions, or was that it?
There's one more, which is where the classes map as well as the overall BPS.
Yes. So the BPS classes, or succession classes, were mapped, and the biophysical settings are mapped. And the most useful way to use them, because they come as two separate grids, is you just combine them. So if you combine the BPS and the S class, you can see, for example, if you were looking at the mixed conifer in California, you could see that biophysical setting, and then you'd see the classes that are associated with it. And in fact, doing that combine is exactly how we determine what the current condition is for these biophysical settings. That's the current condition. The model gives us the reference condition, and with those two, we can measure vegetation condition class. And then I guess also just to mention on the succession class and the biophysical settings data, when you get those as spatial data, the succession classes just say A, B, C, D, or E. There's a letter name associated with each class. And the biophysical setting will have a name and a code associated with it. And what you really need to do is bring up the BPS model description, like the ones I showed today, to understand what that means. What is Class A here? And that's where you bring in that description document and get that information. The hills, what was done, and I don't think I clarified this, so I'm glad you've asked the question. The Bodie Hills, they, I believe, did their own remote sensing, so they mapped biophysical settings. They didn't use LANDFIRE data, and they mapped succession classes. So I guess I'm not sure. Each system apparently has one BPS class. There should have been multiple classes, succession classes, for a given biophysical setting.
Wrap up. So again, reminder, I will send an email out to everyone who registered on the consortium website with the links to the recordings once they're ready and edited. And that same page will also have a PDF of these slides. All right. With that, unless there's anything else, I wanted to give a giant thank you to LANDFIRE, Jeannie, and of course our wonderful speaker, Kori, who did a great job at demystifying all these questions. So thank you very much, everyone, and have a wonderful rest of the week.